The Bronsted-Lowry model of acids and bases states that acids are substances that are capable of donating a proton, and bases are substances that are capable of accepting protons. Now this means that there are substances that we would not normally think of as acids or bases that function under this particular model. For example, the Bronsted-Lowry base ammonia, NH3, is not what we consider a base under the Arrhenius model. It's not a hydroxide. However, as stated before, NH3 is capable of accepting a proton and becoming the ammonium ion. Now when we start to look at acid and base reactions, we'll start to see occasionally the appearance of, this is slightly unusual when it comes to we're looking at an acid-base chemical equation. We see an arrow, and normally we're used to seeing the arrow drawn pointing only to the right. But in these cases we see the arrow is pointing back to the left as well. This is called a reversible reaction. That means that if we read the reaction from left to right, it shows ammonium acting like a base, accepting the proton, and becoming ammonium. However, if we read the reaction in this direction, basically backwards, we show ammonium donating a proton and leaving behind ammonia. So this concept of reversible reactions kind of leads us to the topic of what's called a conjugate acid-base pair. Now, before we get any deeper into the topic, we have to discuss a couple of terms that will be important. The first term is the hydronium ion. The hydronium ion is created when water itself behaves as a Bronsted-Lowry base. Now we don't normally think of water as being acidic or basic. The reality is that water is both acidic and basic, which we'll discuss momentarily. So if water behaves as a Bronsted-Lowry base, it can actually accept a proton and become H3O+. This is called the hydronium ion. It's often used interchangeably with H+, as we'll see in our next section where we discuss pH, which is a measurement of concentration of hydrogen ions. Because if we have a solution of water, some of the water is going to pick up H+ and make H3O+, and some of it's going to go the other direction. Okay, so the amount of H+ and the amount of H3O+ is always going to be identical. The second term is the word amphoteric. Now I just said that water has the ability to act as both an acid or a base. And that's exactly what the definition of an amphoteric substance is. So an amphoteric substance is one that can act as an acid or a base under the Bronsted-Lowry model. Okay, so we said that water is an example of that, H2O. So if H2O is being an acid, that means it's donating a proton and leaving hydroxide behind. If water is being a base, water is accepting a proton and creating the hydronium ion. Okay, let's look at a couple. This is another example of a amphoteric substance. This is called the bisulfate, or the hydrogen sulfate ion. So if it's acting as an acid, then it's going to donate its proton, leaving SO4 minus 2. Oh, excuse me. That's it. Boo-boo. Got a little ahead of myself there. Okay, if HSO4 is behaving as a base, going to add H plus. It's going to create H2SO4. So this is an amphoteric substance, any substance that can act as both an acid or a base under the Bronsted-Lowry model. We do see these occasionally. Okay, so what we have here is we have some relationships here between the acid and the substance that is created when the acid donates the proton. And here the base, the relationship between the base and the substance that is created when the proton is accepted. These are called conjugate pairs. So the acid and the substance created when the H is donated are conjugate pairs, and a base and the substance that's created when the base accepts a proton is another conjugate pair. So an acid will become hydrogen and what's called the conjugate base. A base, when it accepts an H plus, will create what is called the conjugate acid. So every acid has a conjugate base. Every base has a conjugate acid. So let's look at a few examples. Here's hydrochloric acid. Hydrochloric acid will become H plus. And then what's the conjugate base? Okay, well, if we take the H off, we have Cl. And if we're taking off positive 1, say this is 0, so we're going to remove positive 1, so we're going to subtract 1 from the oxidation number. So it's going to become negative 1. So this is the acid. And this is, so chloride ion is the conjugate base of hydrochloric acid. Well, why do we call it a base? Well, remember, this is a reversible reaction. So if we look at the reaction going this direction, it looks just like an acid. Okay? Instead of being an acid creating H plus and a conjugate base, now it's an ion that's going to accept H plus, which means that that's the definition of a Bronsted-Lowry base, making the hydrochloric acid. So if you read one direction, you say, oh, this is an acid. If you read the other direction, you say, oh, this is accepting the H plus back, so that means it's a base. Okay, let's look at another example. Let's look at ammonia again. Remember, ammonia is a weak base. Anything with an amine group, NH2 or NH3, is a base. Okay, and when it does, remember, it's NH4 plus. Okay, so here NH3, so I'm adding an H, and I'm adding a positive charge. This was 0, adding 1, so it goes to 1. So this is a base. So this makes ammonium ion is a conjugate acid. Now, a lot of times when we look at organic acids, we look at, see their formulas are written a little bit unusually. This is a very simple acid. It's called formic acid. And this formula looks unusual because the two O's that are in the compound are separated. You would think it would be written CO2H. The reason they're written separately is to illustrate the fact that this O and this O are different somehow. If we drew the Lewis dot structure for this, this is what we would see. Sorry, I forgot an H here. Okay, so this is formic acid. So rather than saying H2CO2, you see the O's are separated in the formula because they're bonded to the carbon in a very different way. This one's double bonded. On this side, the oxygen is just single bonded to the carbon, and it's single bonded to the H. This H right here is the acidic H. This is the one that comes off to make H+. This H does not come off of the carbon. This is a non-polar bond. This is a very polar bond. Remember, OH bonds are usually indicative of hydrogen bonding, which means that there's a very strong dipole that exists here. This is very negative N, this is very positive N. I mean, the H plus comes off very easily because it already feels kind of like H plus, even though it's bonded to the oxygen, and it is not a complete positive charge until the H is released entirely from the molecule. So when you encounter this type of a formula, you sometimes see H's that are separated from each other and O's that are separated from each other. Okay, this COOH is called a COO group, which is a carboxylic acid group, or carboxyl group. So it just indicates that this here H on the end, this is the acidic hydrogen. So how can we figure out what is the conjugate base of formic acid? Well, we know that it's going to make H plus. Okay, this is the H is going to come off, so what's left over? HCOO. Okay, well, we took off the H, so we dropped off the H here, and we're taking off one positive charge, so it's going from 0 down to -1. So HCOOH, or formate, is the conjugate base for formic acid. Okay, so remember, if you have an acid and you're trying to find the conjugate base, take off an H, take off one positive charge. Okay, let's do one more quick example. Okay, let's look at H2PO4 minus. And if you're told this is an acid, let's ask ourselves, how do we find the conjugate base of H2PO4 minus? We know it's going to make H plus. So we're going to remove one of the H's. So instead of H2PO4, it's going to be HPO4. We're removing one positive charge. It's already -1. We're going to take away a positive charge, so we're going to make it -2. So this is the conjugate base. Okay, lastly, we talked about the strong acids, the ones that dissociate 100% in water. Remember, there's 6 of them that you must memorize. Strong acids have weak conjugate bases. Weak acids have strong conjugate bases. So HCl is a strong acid. Remember, its conjugate base is a chloride ion. So that means chloride ion is a weak base. Hydrofluoric acid, on the other hand, is a weak acid. That means that very little of it dissociates. What does dissociate produces H plus and F minus. That means that F minus is technically a strong base. Okay, now remember that weak and strong are relative terms. Okay? All you need to memorize is the 6 strong acids. And this is just something to know, that there's a relationship between the strength of the original acid or the original base and its conjugate. So its conjugate is going to have the opposite. Okay, now it's your turn to practice finding conjugate acids and bases.